Before you move on with this video, here's a list of 7 important trigonometric identities that you must know before watching this video. If there's even one identity that you're not aware of, pause the video, memorize it, write it down on a sheet of paper, and only then move on with your questions. Now, when you start proving trigonometric identities, your first step should be to start with the more complex side. What do I mean by this? So say I had the equation 1 minus cos² x upon sin x. I have to prove that this is equal to sin x. Now, my first job is to start with the more complex side. This is to say that I find a side where I have a fraction, a power, a multiplication. There is some operation happening that I can actually play around with. Because if I have sin x, if I start with RHS, sin x is RHS, 1 minus cos² x by sin x is equal to my LHS. If I start with RHS, which is I try to prove that sin x is equal to 1 minus cos² x by sin x, my job gets really hard. So first, start with the more complex side because you can do much more things with it. Now that's the first thing. Second thing is to you either isolate or rationalize or simplify. These are the three options you'll have for almost all of the trigonometric identities. Now before that, the first thing that you need to keep in mind is trigonometric identities. So when you're proving trigonometric identities, you don't actually operate on them. What do I mean by this? If this was my identity, I can't take sin x to this side and be like 1 minus cos² x is equal to, because I multiplied sin x with sin x, is equal to sin² x. Hence, I've proven the equation. No, that cannot happen at all. The entire point of proving trigonometric identities is that you isolate one side and you apply some operation or you simplify some equation to match it with the other side. So in this case, our RHS will stay in isolation, will stay constant, we will not do anything to it. That's why our third step would be to match with other side. So my last step in proving this identity would be to match my RHS to match my LHS to my RHS, and I will not do anything else. Now let's start. If this was my equation, 1 minus cos² x by sin x, I have to prove that it's equal to sin x. We are using a trigonometric identity here. In the beginning of the video, we saw that sin² x plus cos² x is equal to 1. If you don't know this identity, go back to the beginning of the video, have a look at the list of 7 identities that you must know before starting to solve or starting to prove trigonometric identities. Now here, you need to look for a pattern. In the question, I have a cos, but in the answer, which is my RHS, I only need a sin x. So I need to find some way where I can change my cos² x to a sin² x. The only way I can do that is through this identity, which says that sin² x plus cos² x is equal to 1. I know that if I have to get 1 minus cos² x in this equation, I just transpose cos² x to this side to get that sin² x is equal to 1 minus cos² x. Now here we use this equation, we simplified this into this form. But in an actual exam, you should have this on the tip of your fingers. That sin² x is equal to 1 minus cos² x and cos² x will be equal to 1 minus sin² x. So if you ever see any of these two, that is 1 minus cos² x or 1 minus sin² x in some other question, the first thing that you need to do is to simplify it to sin² x or cos² x respectively. Now that this is sorted, let's substitute sin² x into this equation. So we have sin² x upon sin x. I have to prove that this is equal to sin x. Now this is rather simple. Sin² x can be written as sine x into sine x upon sine x. I can simply cancel these two out to show that these two are equal. We know that LHS is now equal to RHS. You, you don't actually have to show this step in an exam. I'm just doing this to show that this is how we cancel out stuff. Now let's move on to a more complex example. So say I have the equation 1 minus cos x upon sine x is equal to sine x upon 1 plus cos x. What was our first step? Our first step is to find the more complex side. Now, realistically, both of these sides are pretty similar, but we're going to choose LHS just because there is a negative sign in it. And in general, negative numbers or a negative operation in an equation is a little more complex to deal with than a positive sign. So, we're going to start from LHS and we're going to slowly match it to RHS. Now, what is our pattern here? We know that in the question itself, I have a cos x, I have a sin x. I have to prove it into a sin x and cos x. So essentially, there is no square in this equation. I can't cancel anything out. So in this list, where I could either isolate, rationalize, or simplify, I know I can't simplify. Isolation is basically taking things common and cancelling them out, which I really can't do here. I mean, I have nothing to take common. I can't cancel out anything because note that this is not a cosec square. A lot of kids make this mistake in their exam. They write sin x plus cos x is equal to 1. This is completely wrong. Only sin²x plus cos²x is equal to 1. So this is not equal to sin x. You cannot write it like that. Now, we know that we can't isolate, we can't simplify, so the only thing we can do is rationalize. Now, what does it mean to rationalize a trigonometric identity? Just because you guys have made it so far into trigonometric identities, I'm assuming you all already know the concept of surds, which is basically, if I have the surd 1 upon root 2, I can write this as 1 by root 2 into root 2 by root 2, which is called rationalizing the denominator, because essentially I don't want a root sign in the denominator. So I multiply both the numerator and the denominator by the same number, which is root 2, to get a integer value for the denominator. Similarly, if I had the fraction, say 3 by 5, and I multiply both the numerator and the denominator by 2, I get 6 by 10, but 6 by 10 is also equal to 3 by 5. So I can multiply both my numerator and denominator by the same number or the same identity, but I will still get the same answer. Similarly, I will multiply my denominator and my numerator with another identity or with another number so that I can actually play around with it. I can get some square, I can take out something common to match it to RHS, because currently there is nothing I can do to this equation. That is, I cannot simplify this any further to get RHS. Correct? So, just like we rationalize, we're going to multiply 1 by cosec upon sin x with sin x upon sin x. So I multiply sin x with numerator and I multiply sin x with denominator. Now, look for a pattern yet again. You see on the RHS side, in my numerator, I have sin x, which means that I'm taking sin x common. This thing needs to get cancelled out with the denominator. I cannot have a cos x in my numerator, correct? So I will not multiply this with individual element. That is, I will not do sin x minus sin x cos x. I will keep sin x common outside. I will not multiply it with the bracket. Because what's my aim? I want sin x to be there in the numerator. So I want 1 minus cos x to get automatically cancelled out by the denominator. Now similarly, Sin x into sin x is equal to sin²x. Now what did I tell you earlier? If I ever have a sin²x or a cos²x, you will immediately use the identity sin²x plus cos²x is equal to 1, from which I know that sin²x can be written as 1 minus cos²x. This is an incredibly important identity that you must know. Now, I can write this as sin x 1 minus cos x upon 1 minus cos²x. Now still, look at the pattern here. I want to cancel 1 minus cos x in my numerator, and I want to 1 plus cos x in my denominator. Now what can I do to this to get RHS? Very simple. If I had an equation which is a square minus b square, we know that this can be written as a plus b, a minus b, correct? Similarly, if I had 1 minus cos²x, I can also write this as 1 square minus cos²x, because essentially 1 square is equal to 1. So I will use this identity and replace 1 minus cos²x with 1 plus cos x, which is a plus b, into a minus b, which is 1 minus cos x. I know that I can cancel these two terms out to get what? Sin x by 1 plus cos x, which was initially our RHS. So LHS is equal to RHS, and our identity is proven. So let's go over it again. What did we do? We chose the more complex side where we had a negative sign. Second step was to look for patterns. We saw that there is a sin x in the numerator which we didn't have already. So we had to do something to get a sin x in the numerator. We know that we have to choose from these three. We can either isolate, rationalize, or simplify. Isolation and simplification don't really apply here, so our only option was to rationalize. We saw that in order to rationalize, we will multiply both my numerator and my denominator with the same trigonometric identity or a number or any. Then in order to rationalize, we will multiply both our numerator and denominator with the same trigonometric identity. So 1 minus cos x upon sin x was multiplied with sin x in the numerator and sin x in the denominator as well. Now again we go back to our equation that we have to prove it to. Now again we go back to our RHS. We know that we do not want a cos x here, we only want a sin x. So there was no point in multiplying this individually with both of the elements. Like, there was no point in writing our numerator, only the numerator, as sin x minus sin x cos x. Because I don't want a cos x in my numerator, I only want a sin x. So I can take it out common and hope that my 1 minus cos x will get cancelled out with my denominator. And it did. So here we isolate sin x outside, keeping 1 minus cos x inside, upon sin²x. We saw that sin²x can be written as 1 minus cos²x, using the identity that sin²x plus cos²x is equal to 1. So we just substitute this value into 1 minus cos²x. Now again, we go back to RHS. This thing says that there is not a square sign in the denominator, which means that my cos x must simplify. So I can use the identity a square minus b square, which can be written as a plus b, a minus b. Using this to write 1 plus cos x and 1 minus cos x, these two can get cancelled and we're left with RHS. Okay, now let's move on to an example where we go beyond sin x by cos x. Okay, now let's move on to an example where we go beyond sin x and cos x. So say I had the equation 1 minus cos² x upon cosec²x minus 1, we have to show that this is equal to tan²x into sin²x. Now, first step is to choose the more complex side. We know that there's a lot going on in LHS. We have square, we have the subtraction sign, it's in fraction. So LHS is definitely the one we're going with. So we're going to be playing around only LHS. RH is going to remain constant. That's our first thing. Our second thing is that we have three options. Either we could simplify, or we could isolate, or we could rationalize. We can see that there is a lot of simplification that can happen here. Because right from the top of your head, you should know that 1 minus cos²x is equal to sin²x, as we discussed earlier. 1 minus cos²x should be equal to sin²x. So we know that we can definitely simplify this equation, correct? So simplification is what we're going for. So our numerator is simplified already. We know 1 minus cos²x is equal to sin²x. Now let's look at the denominator. If in case you do not know an identity which involves cosec²x, which is the reciprocal of sin x, we know that cosec x is equal to 1 by sin x. If you do not know about an identity which involves this, please go back to the beginning of the video, have a look at the 7 identities listed there, and quickly learn them and come back to this section. Now, let's look at this. The identity was that cosec²x minus cot²x is equal to 1. Can I get a cosec²x minus 1 from this equation? Yes. I just have to transpose 1 to this side and I'll take cot²x to this side. So I get cosec² minus 1 is equal to cot²x. Correct? I can simply write cot²x here. So this equation can then be written as, or this identity can then be written as 1 minus, so this identity can then be written as sin²x, which is how we write 1 minus cos²x, upon cot²x, and we have to prove that this is equal to tan²x into sin²x. Now, we know that we only have things in terms of tan x and sin x, which means that there is no cot in our RHS. This means that we have to simplify, correct? What do we know? We know cot x is the reciprocal of tan x. We want to get an equation that is in terms of tan²x and sin²x. We know that cot x is the reciprocal of tan x, correct? So cot²x would also be the reciprocal of tan²x, correct? So I can write this as sin²x upon 1 upon tan²x. Why did we do this? Because we know that on RHS, we're only dealing with tan x and sin x. There is no place for cot. This can then be written as sin²x is getting divided by 1 by tan²x. We can multiply this with its reciprocal, getting tan²x into sin²x as our final answer. So LHS is equal to RHS.